So, now the question is how do we generate V PTAT? So, somebody basically made this this observation. So, let us say you take a current I and push it through a diode, we call this I1 and let us call this VD1. And we and let us take the same current I1 and push it through, let us connect N diodes in parallel. Okay, let us call this voltage developed here as V, let us call this VDN. So, what is VD1? Phi t ln I1 by Is. N diodes connected in parallel is equivalent to, or what will the current be that flows through each one of these N diodes? I1 by what is the current that flows through each one of those N diodes? I1 by N. I1 by where is NIS coming from? What is the current flowing through each one of those N diodes? Do you understand the question? What is the question?
What is the current flowing through each diode?
Yes. What is it?
I1 by Is.
What are the units of I1 by Is? What is the question that was asked? What is the question, man? Forget about the answer. What is the question?
What is the current flowing?
Yes, can you please answer the question?
I1 by N.
That's all. What is this that you're going around and round in? Is it clear, folks, or it's not clear? You have current flowing through N identical diodes, correct? So, what is the current through each one of them? I1 by N, correct? So, what is VDN? Phi t times ln of I1 by NIS. All right. Is that clear, folks? So, now what is VD1 minus VDN? Phi t ln N. Is that clear, folks? Okay. And what is phi t itself? We saw that. So, VD1 minus VDN is KT by Q times ln N. All right. So, what is the temperature behavior of VD1 minus VDN? It is directly proportional to absolute temperature, correct? Okay. So, but we need, I mean, we need something proportional to absolute temperature, but we also need its temperature coefficient to be plus 2 millivolts per Kelvin, because it needs to exactly compensate the negative 2 millivolts per Kelvin due to the diode. Okay. So, what is the temperature coefficient of this guy? In other words, what is d by d capital T of VD1 minus VDN?
K by Q times
Yeah, K by Q times ln n, which is Kt by Q ln n by T, right. So, what is at room temperature, right, which is 290 Kelvin, Kt by Q is 25.8 millivolts, right, divided by 290 ln n. So, how many this times ln n,
88.9
which is
88.9
88.9 microvolt per Kelvin times ln n. Okay. So, therefore, what we need to do, what do I mean, but we need 2000 microvolts per Kelvin, correct. Okay. And so, what should we do? How do we increase the temperature coefficient? The number of diodes, if you want to increase, okay, so one idea is to increase n, correct. So, if you want to increase, you need to increase ln n by for 2. If you want to make 88, if you want to multiply it by some number and you get 2000, what should you multiply that? What should that number be? Which is how much, man? Something like 22 or 23, right. So, what is e to the power 23? Huh? 9.7 billion, right. So, to increase the number of diodes to make this to get 2 millivolts per Kelvin, you need 9.7 billion diodes, right. Okay. All right. So, that's obviously not practical. So, what do you think we can do? Can somebody think of a simpler way?
Change the current in that n diodes, like that was I1.
Okay.
You can tweak it so that the ln into n, the ln will be n into something.
Yeah. So, well, that n into something must be 9.7 billion, right. Of course, now you say, no, I will only have I will have only a million diodes, but then I will have 1000 times the current, right. That also does not make sense. Okay. What is the simplest thing that you can think of? you just amplify, correct. So, if you multiply VD1 minus VDN by a number m, what is the temperature coefficient? M times 88.9 millivolt per Kelvin times ln n, correct? Sorry, microvolts. Okay. So, this way, so what should m times ln n times 88.9 microvolt per Kelvin must be equal to, exactly equal to, we must choose m and n such that m ln n times 0.9 microvolt per Kelvin equals 2000 microvolts per Kelvin, which is basically the negative Tc of the diode, of the forward biased of VD1. So, what must m ln n be? Twenty 4. Can you check if kT by Q is actually 25.8 at 290 or 300? What is K? K is 1.38 into 10 power minus 23, T is 290, Q is 1.6 into 10 power minus 19. What is kT by Q at 290? What is kT by Q at 290 Kelvin, man? Twenty-five. Okay, so basically at 290 it is 25 millivolts. It's 25.8 at 300 Kelvin, I think. Okay, so what is the this 88.9 is therefore not correct. 25 millivolts by 290 is how much? It is 86.2 microvolts. So, this is also 86.2 microvolts. So, what is m ln n?
23.2.
Okay. So, I'll round it off to 24. Okay. So, Vd, therefore, m times Vd1 minus Vdn must be approximately, which is basically m phi t ln n, right, or m ln n phi t if you want, which is, and m ln n is what, approximately 24. Do you guys folks understand? You understand?
Like m ln n is 24 that.
Nice. You look at, I see a totally blank expression on your face. That's why I'm asking. What is bothering you?
I was writing down.
You understand what I'm saying, right? Is it clear so far? Right. So basically, Vd1 minus Vdn is phi t ln n, correct? We are multiplying that by m, and we just concluded that for this expression must have a positive temperature coefficient of Tc of how much? 2 millivolt per Kelvin, correct? So, therefore, m ln n times phi t, m ln n must be chosen to be approximately 24, but m times Vd1 minus Vn must therefore be 24 times phi t, correct, and phi t is about 25 millivolts at 290 Kelvin. 25 millivolts times 24 is 600 millivolts, correct. So, what will be the Vd1, the diode drop is roughly 650 millivolts, correct. So, what will be the VREF that you get with 0 Tc? Do you understand the question? So, basically what are we, I mean, so if we choose m ln n to be equal to 24, the temperature coefficient, the positive temperature coefficient of m times Vd1 minus Vdn will be equal to plus 2 millivolt per Kelvin, right. And what do we need to do? We need to take, to get our reference, the reference must be Vd1 plus m times Vd1 minus Vdn, correct. This and this will be, this will have 0 temperature coefficient, all right, and so it does not matter what temperature you find it, it will always be the, it is supposed to be the same. So, at room temperature we know that Vd1 is approximately, so this must be approximately 650 millivolts plus 24 phi t at room temperature. At room temperature phi t is about 25 millivolts. So, basically plus 24 phi t, which is 650 millivolts plus 600 millivolts, which is 1.25 volts. Okay. So, it so turns out that this if you go through deep, if you go deeply into the physics of the bipolar transistor, okay, you will get this, you can trace this down to the band gap of silicon, this reference voltage to the band gap of silicon, because that Is, right, has got things in it which depend on the silicon band gap and so on. So, the bottom line finally is that this reference can be traced to the band gap of silicon, all right. So, this is called the, this is often called the band gap voltage reference. Is that clear? And it is roughly about 1.25 volts. Okay. So, in other words, so to generate VREF, we need to basically Vd1 plus m times Vd1 minus Vdn okay, which is m plus 1 times Vd1 minus m times Vdn, correct? Yes, no? All right. Okay. Now, remember this, what is Vd1? Voltage across with current okay, VDN is the current voltage across the same diode with current I by N, which is also the same as voltage across N diodes with current what? With current. So, rather than go on drawing N diodes, commonly people put just N by the side, and it is understood that you have N identical diodes in parallel. Okay. But the key point is that this diode, I mean this diode and this diode must carry the same current, only then will VD1 minus VDN be phi t ln, right. So, only when, remember that only it is only when VD1, I mean both the diodes carry exactly the same current, will VD1 minus VDN be exactly phi t ln n, which is the PTAT thing that we want. Is that clear? That is only then when will this factor cancel out when you subtract. Is that clear? All right. So, that is something to bear in mind.